Now, if we're talking about pressure, we need to figure out how that pressure changes. And first off, why in the world am I actually feeling pressure? Well, if you've ever been swimming before and you go into a swimming pool, what you probably realize is that you feel a lot more pressure when you're on the bottom of the pool, if you're like just sitting down right here, than you do when you're up here. I need to get really good at drawing sitting people and stuff. As no, I can draw way better than this, but I'm making a video. I'm not going to spend 10 minutes drawing something. Quick sketches. That's my New Year's resolution. Okay, so the pressure increases as you go down lower. Now why? Why is that? Well, what you're feeling is called hydrostatic pressure. This is the pressure you feel right here. Okay? And if you want to figure out absolute, you simply take atmospheric plus this. It's the density of the fluid times gravity times the height. In effect, what you are feeling is if I have, I'm underneath the fluid right here. Hydrostatic pressure is simply me taking all the weight of the fluid above me and dividing it by the area of my body. Okay? So weight over area. This is equivalent. You can actually do a derivation for it. And it just, in the end, the simplest way of doing it is figuring out this way. Okay, we'll get rid of that right there, and we're good to go. Now, why do we need this? Because this is incredibly important when it comes to hydraulics and other things, and also it's how we measure things like fluid velocities, measure the heights of very tall mountains. We do it using hydrostatic pressure. Instead of it being water, though, we're dealing it with when it's air. Another thing to think about is that since it changes with height, it means it gets more and more as we go to the bottom. So here is a fun little question. Let's say that this right here was a door, okay? Where should I put the hinges for that door? Should I put them at the top or at the bottom? Which one would make the most sense? The correct answer is actually at the bottom. The reason for that is because the hinges are going to be resisting the force, and the most force is happening at the bottom. As I go up, the force decreases. I want to have as small a moment here at the end of my door as possible. So if I want to have as small a moment as possible, I need to make sure that my moment, which is equal to force times distance, is as small as possible. And so my smallest force is at the biggest distance, rather than my biggest force being at the biggest distance. Cool little problem. Fun little application of this. Okay. Now, if I'm talking about just a room here, the amount of pressure change due to, hydrostatic air pressure is negligible from the ceiling to the floor. Technically, there is a slight difference. Like maybe the top of the room is 1 atmosphere and at the bottom it's 1.006 atmospheres. But I can't feel 0.006 difference in atmosphere. However, in a liquid, I'm going to feel that difference much more quickly. The reason for that is because liquids are much more dense than air. Air is like 1.225 kilograms per meter cubed. That's for air. That's the density. For water, it's 1,000 kilograms per meter cubed. So water is 1,000 times more dense, and therefore I feel it 1,000 times earlier than I would with air. Now, what do you think would happen if I had 3 fluids on top of each other? Fluid 1, fluid 2, fluid 3. We'll say that they are all separate. They're just staying by themselves. And I'm sitting here on the bottom. How could I calculate the pressure that I'm feeling? What would it be like? Well, the answer is not all that complex. In fact, what it is it's simply adding up the hydrostatic pressure from all of them. So I could get, P1, P2, P3 separately and add them all together. And if they all had the same density, well, I could just add the heights together. But we're assuming in this case that they're all 3 different fluids and they have 3 different densities. And so I'll just feel the hydrostatic pressure from each of those, add it to my atmospheric pressure, and I would have my answer. One last little, well, I guess not quite last, yeah, one last little detail here, I think. Let's see, am I right about that? Yes, I am right about that. Is that if I have the same reference point for the height of the water, so long as the water is considered to be flat, no matter what the architecture looks like underneath, no matter how crazy this shape is, it doesn't actually matter. That's not going to change the hydrostatic pressure I feel. All that matters for me is, am I at the same height? If I'm at the same height, then I will feel the same hydrostatic pressure. So A, B, C, D, E, F, and G, they all have the exact same pressure. H and I, however, do not, even though they're at the same depth, because H is also under some mercury. Why is there a random pool of mercury at the bottom of this pool? I have no, but I'm terrified to find out. Okay, so that's it for this time. Next time we're going to be doing an example where we have a really fun time seeing how we can apply these hydrostatic pressure equations. So thank you all so much. See y'all later. Bye-bye.